the momentum behind the adoption of deep learning is really quite staggering. If you look at it from startups with just a few tens of millions of dollars of funding, just a few years ago, 5 years ago, has now grown to $6.6 billion. The number of papers that are published around the world on deep learning has grown to 3,000 this year. Now, 3,000, the way to think about that is if 1 out of 100 researchers' work is worthy of being published, imagine the number of people who are doing deep learning research. And you could just see that in the Neural Network Conference, the International Neural Network Conference. NIPS is Neural Information Processing Systems, basically neural network artificial intelligence conference. Over the years, look at the attendees when they register. This year, long before, literally a month before the conference starts, a general purpose panic to register. I think only David Hasselhoff in Germany can attract this level of enthusiasm. Huh, guys? David Hasselhoff. He might actually be in the back. I'll just have him come on as a guest. So you could just see the adoption of deep learning and the momentum around AI. And the type of work that's being done just spans so many different fields of computer science and different fields of science. There's healthcare, enormous amount of research being done there. Robotics, enormous amount of research being done there. Natural language understanding. Speech recognition is taking the words that come out of my mouth, the sound, and translating it to text. Sound to text, speech to text. That's speech recognition. But what did I say and what did I mean? That's natural language understanding. Natural language understanding, obviously, is much, much more complicated. A very deep area of AI, lots and lots of work being done there. If natural language understanding could be cracked, could you imagine how it's going to change the way customer service is done, how we interact with computers? Incredible, incredible opportunities. The number of research work is just really shocking. And people are solving these problems that we've, for the longest time, felt was impossible to solve. And so today I want to show you a few that are just kind of fun. It's easy to understand, and when you think about it, there's the oh my gosh moment. The first example is done in NVIDIA research. What's happening here is a form of computer graphics that's photorealistic but takes a long time. It's called ray tracing. We're simply literally following a ray of photons as it bounces all over the room, eventually coming into our eyes. Well, it takes a long time to literally trace each one of those photons, and that's why when you see those white dots and black dots, that's when the computer graphics is not complete. Well, we taught an artificial intelligence network how to finish the job. And the way to think about that is, if I showed you this incomplete picture, I bet all of you could figure out what is the best color to put into that dot. Somehow, we figured it out in our brain. Well, we taught a computer how to do the same thing, and it literally filled in the noise. Imagine what you could do with this thing. Using the same autoencoder architecture, you can now take an image that is very low in resolution and enhance its resolution. From absence of information, we can create information that fundamentally breaks information theory. From the absence of information, we can create information, which is what's happening there. And so you can increase resolution if you have a photograph that's ruined. Parts of it was ruined. We can go back and fix it. Just by you looking at it, if you could figure it out, we can probably teach an artificial intelligence how to do the same thing. Here's another one.
Listen up. Train your warehouses is our main objective. Now, like say, you and your men will do that. You have to go in and out very quick.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and large stone.
And so this is what's
The
happening.
avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
So this is what's happening.
Listen up. Train your warehouses.
If I could just get you to stop. So this is what's happening. Imagine lip reading. You learn how to look at the animation of somebody's face, and you can imagine the words that is being said. This is the inverse of lip reading. We had the artificial intelligence network look at a whole bunch of videos of somebody talking, and from it, it can now infer what is the animation of the face from the words spoken. What is the animation of the face from the words spoken? Okay? Like lip reading, except backwards. This one is called pose estimation. Pose is your 3D posture. How are you posed? How are you positioned in 3D space? Well, we have to teach, if you were to look at a video, you can probably infer what is the pose of that character in 3D space. However, how do you teach an artificial intelligence network to do that? How do you write software to look at a bunch of ones and zeros in a video and recognize where is the person and what is that person's three-dimensional pose? From 2D to 3D pose. If we were able to do that, we can recreate that character in 3D world looking at the video. So shining a camera on top of me, I can now capture me and beam me into virtual reality. So imagine the holodeck next time. There'll be a video camera just looking at me, and somehow I warp into this virtual reality world. Wrench is doing amazing work in pose estimation. This is really cool. This is a 3D animation character. This is a virtual reality character. And based on whatever you throw in front of it, it figures out what's the best way to animate, to navigate the course. You see what's happening? So it learned how to climb, learned how to hop off, all completely based on artificial intelligence. And smart enough not to walk into that. And as it tiptoes through this little tiny bridge, just like we would do. A virtual character taught AI. And then this last one, before I show it to you, it's a robot that learned from an example. This is Peter Abiel's work at UC Berkeley. He goes into virtual reality. He shows the robot how to stack bricks just a few times with just a few examples. This is what I want you to do. Stack bricks. And now, it doesn't matter where the bricks are located. Robot figured it out. One-shot learning, imitation learning, basically how we learn. So this is the actual robot stacking actual bricks, and this is how it learned it in virtual reality. Okay, just some examples of what AI is able to do. None of these examples have we been able to write software to overcome for the longest time. Just imagine writing software to solve these problems. And now finally, We use this artificial intelligence approach called deep learning. We feed it tons and tons of information, and somehow these deep neural nets learned. Well, the work that is being done in deep learning is literally all over the world. There are just so many researchers doing deep learning work, and we're just delighted that we are the deep learning platform for modern AI. There are all kinds of platforms that are being used, all kinds of frameworks and tools that are being used. PyTorch and Paddle of China, Chainer of Japan, MXNet that Amazon uses, Cafe2 that Facebook uses, Microsoft's Cognitive Toolkit, CNTK, Theano, and TensorFlow from Google. The number of industries that are advancing AI in research and now in startups all over the world. We're working with some close to 2,000 startups all over the world in all these different industries, all developing on the NVIDIA platform. Now, our strategy and our commitment is to continue to advance with all of our might the ability to develop better, smarter, more complex AIs faster. Now, the reason why, even though we've advanced computing now, advanced AI research by a factor of 100 in the course of the last 4 years, we've improved performance by 100 times in 4 years' time. Deep learning has been completely revolutionized because of the GPUs. However, we believe that we need to improve the performance by so much more. And the reason for that is simply this. We want to make it possible for these AIs to learn how to write software itself, but to have AIs create AIs itself. And therefore, we need these massive supercomputers just churning away, trying all these different types of algorithms, and having software write software by itself. Just 2 weeks ago, just about the entire world's computer industry adopted Volta, our latest generation GPU. Volta is now available in every single cloud on the planet, from Azure to Google Cloud to Amazon Web Services, Alibaba, Baidu, Tencent. It's available everywhere, anywhere on the planet. As a result, all of these startups that are working on NVIDIA's platform no longer need to build their own supercomputer. They could go rent one in the cloud. And as they grow and their workload continues to increase, at some point they might decide to buy their own supercomputer, and every single computer company in the world now offers the NVIDIA Volta GPU for their GPU servers. From IBM, HP and Dell, Cisco, Lenovo, and Huawei. Basically, the NVIDIA GPU is everywhere. It's everywhere in every computer, every single PC, in every single region, available in every single cloud. And so we're going to commit to continue to advance this computing platform. The fact that we have one architecture makes it possible for your software development and for the company that you create to be able to enjoy growth every place on earth. Using one architecture, using one singular architecture, you could develop on NVIDIA and scale on NVIDIA all over the world. Okay? So the world's AI platform. Well, the next major challenge is after developing the AI, you have to run the AI. Developing the AI is called training. Running the AI, running the deep neural net, is called inference. To infer from input some insight about the future, whether it's classifying the image, recognizing things, recognizing voice. It could be predicting what future securities are going to be. It could be detecting fraud. somebody who is trying to break into your company. So these deep neural nets are trained on NVIDIA platforms. Now, the big challenge for us is to make it run incredibly efficient across all of the world's computing platforms. Now, this is an area that some people call IoT, but I see the world developing in 3 different ways. The first is that the AI network will run in the cloud. And these computers are massive in scale, 10 megawatts, 20 megawatts data centers, and they're running and inferring and basically running queries from billions and billions of people who are accessing the cloud at the same time. There's another class of device way on the other side that we're actually quite familiar with today. Things like Fitbits, Nest thermostats, your phone, all of these little tiny devices that have a little bit of intelligence inside. And that little intelligence network could be voice recognition, it could be image recognition, it could be recognizing your heart rate, measuring your blood pressure, measuring the tremor on a piece of equipment, and recognizing that that tremor is going to lead to failure in about a week's time. And so instead of waiting, when that machinery goes down, you might send somebody out to repair it in advance. And so it's called IoT, and I believe over time there'll be trillions of these devices. And then there's a class of machines in the middle. They're not exactly supercomputing clouds. They're not intelligent sensors, but they're autonomous machines. These machines need to operate and be intelligent and do smart things even when they're not connected to the cloud at all. For example, a self-driving car. You would really, really appreciate it if your car drove safely by itself, even without internet connection. It could be a drone that flies out to find somebody who's lost in a forest. It could be the drone inspecting pipelines, or going through and looking at a forest fire, or it could be somehow inspecting your plot of land and all the food that all the farming that you're doing, and looking for whether there's a disease that has broken out. It could be manufacturing robots. It could be these little drones that people are starting to develop for the last mile of delivery. As a result of the Amazon effect, where more and more of us are basically buying products online and hoping that it would be delivered to your house, the number of truck drivers in the world can't possibly serve all of us buying products online and hoping for it to be delivered that same time. And so companies all over the world are building these last mile delivering pizzas, delivering soy sauce in China, delivering a hamburger to your house. Okay, so autonomous machines. All of these are going to need AI inside them. And so the question is, how are we going to be able to support a world where you only have a few milliwatts of power on the one hand, to something that has to be completely autonomous on the other hand, and then of course data centers. The number of different types of devices that we have to support is exploding. The networks that we're supporting is exploding. Starting with CNN. CNN's convolutional neural networks is a neural network that magically figures out what are the important features that represent a particular object or a particular pattern. And it has this ability to learn the features by itself and to generalize that information, so that even if you change the color, the shape slightly, the orientation slightly, it still recognizes it to be the thing that it learned. So you could have a cat be partly occluded and it still recognizes it. You could have a cat change colors, wear a hat, and it still recognizes it. The recurrent neural networks learn sequences, speech, etc. And this one is the revolution that came out recently from Ian Goodfellow. He created this thing called the generative adversarial network. You have one network that's trained to be a master detector. You have another network that's trying to fool this master detector. These two neural networks, one of them generating fake ones, the other one detecting the real ones. So it could be an piece of art, for example. One network generating fake art, fake Picasso, while the other one has been trained to recognize real Picasso. And because the two of them are competing against each other, one trying to fool it, the other one trying not to be fooled, and as they learn and learn and learn and learn and learn and develop over time, one becomes just amazing at recognizing Picassos, the other one becomes amazing at generating Picassos. Two networks, now incredibly powerful, the adversarial network. And then lastly, the recurrent neural net, the reinforcement learning neural net that was used by Peter Beal. And this is basically trial and error. The network is trying over and over again, randomly, initially. Every time it tries, there's a value function that determines whether it's doing it well or not so well. Whenever it does it well, it's encouraged to move in that direction. If it does not so well, it's encouraged to move away from that direction. A value function determines that. Reward and punishment. Recurrent neural networks is how we're going to use, is the basic method for us to train robotics. Explosion of the type of networks. The number of, and this is just a brief view of it, there are so many different designs and so many different architectures coming out. Well, the complexity of the network is growing as well. This little tiny dot, this complexity chart, the size of the area of the circle, represents the number of operations times number of operations, and I just simply multiply the two of them together. Number of operations times the amount of memory that it has to access. Okay? GOPS times bandwidth. That little tiny dot is the original AlexNet just a few years ago that beat every single computer scientist in the world in image recognition. That's that little tiny dot. That little tiny dot, overnight, without learning how to do computer vision, learned computer vision fine enough to beat every single computer vision algorithm expert on the planet in one ImageNet. Completely revolutionized computer vision. If it wasn't because of ImageNet, the work that we're doing here in self-driving cars and robotics wouldn't have nearly progressed as fast as it has. And yet, look at that, over the course of just 4 or 5 years, it has grown. These networks have grown 350 times. This is a speech network, has grown 30 times in the last several years. This one's really exciting. Language translation. I really believe that in a few more years, I'll be speaking into this microphone in English, and it will come out in German. And it will do it completely in real time. And so as a result, that Star Trek Universal Translator is about to happen. The Neuro-Machine Translation Network. Goes in English, comes out German. The network complexity has grown so much. And so what we've done is this. 2 weeks ago we announced a new type of optimizing compiler. It takes neural networks in, and it uses advanced compiling technology and optimizes the network for all of the target devices that it will run. Some of the target devices are very high performance GPUs like the one that I showed you, Volta. 120 tops, 250 watts, powers a data center, all the way to something that's a self-driving car, to a little neural network that goes into a little robot we call Jetson. Just a few watts. It takes input from any framework, any architecture of network from any framework, runs it through this optimizing compiler, and it targets machines that ranges all the way from several hundred watts to several hundred milliwatts. The NVIDIA Tensor RT 3.0. It basically does this. It takes this neural network that's incredibly complicated, this is just one layer, and all the math that goes through it, and we do weight and activation precision calibration first, and then we fuse the layers. Some of the layers could be combined together. Some of the tensors could be combined together. Some of them could be eliminated altogether. And so we fuse the tensors. We do kernel optimization with dynamic programming, tracing almost every single path to figure out what is the single best path for optimizing the speed and the size and the accuracy all at the same time. And we also, of course, have to support multiple streams because sometimes the machine has multiple cameras. Well, the result is pretty amazing. So that's what it does. And this is how well it does it. And so, if you take the CPU, we train the neural network, which is done largely on NVIDIA GPUs today. However, once the network is trained, it's largely run on CPUs today. And the reason for that is because the entire world's cloud is powered by CPUs. And so you train that network, the ResNet 50, now this is 50 layers deep ResNet. The CPU plus TensorFlow, which is Google's framework, runs at 140 images per second. Without TensorRT, without this optimizing compiler, the output of TensorFlow, as we move it into this Volta V100, this GPU here, this does 300 frames per second. However, if you optimize it with TensorRT, all of a sudden the performance just skyrockets. 5,700 frames per second. Because TensorRT optimizes for CUDA and optimizes for the architecture of our GPU, takes advantage of the instructions that we put in here, called Tensor Core, which is optimized for deep learning. For open NMT, neural machine translation, basically language translation, four sentences per second to 25 without TensorRT to 550. Okay? But this is just one dimension of the speed up. 40 times speed up in imaging, 140 times speed up in language. But when you look at the latency, how long it takes in addition. First is how many you could do at the same time. The other is how long does it take for you to do any one of them. In the case of images, we halve the latency. In the case of language, 100 milliseconds versus several hundred milliseconds will make all the difference in whether you can talk to a computer or not, having a reasonable conversation. So TensorRT3, our brand new optimizing compiler. Now, what does it look like in a data center? This is what it looks like in a data center. So suppose you had no GPUs in the data center, no TensorRT. This is 160 CPUs. 160 CPUs will do 45,000 images per second. And this is basically what's happening in the cloud today. Whenever you ask for a photograph, whenever you upload a photograph, this is essentially what's happening. Every single one of those transfers go through some kind of a deep neural network, and it's run on a CPU cluster like this. In this case, 65,000 watts. So 1,500 watts per rack, 4 of those racks. About $600,000 without cables and the top of rack switches and all the power supplies, about $600,000. And this is what it looks like if you bought a GPU. I know, I practically fell out of my seat. You see this? Before. After. Before. After. The more GPUs you buy, the more you save. Just think about that. The more you buy, the more you save. One-sixth the cost, 1/20th the power. 1/20th the power. This will improve your total cost of ownership a factor, an order of magnitude. Before, after. This is the best demo in the world. This is the best demo in the world. This is the only demo that IT department goes, here, do that again. Our IT department goes, oh, Jensen, I love that. I love that. I'm going to make that a screensaver. Just go back and forth, just like that. My kids always, every time, my kids know how cheap I am. They call this save the money. Just one money, save the money. This is save lots of the money. Okay, so that's what it looks like at a data center. But let's take a look at that. Let's look at that in real time. What does it really feel like? Okay, so this is what inferencing is. Now the thing is what's really remarkable about deep neural nets is this is what you see. What the computer saw was a whole bunch of ones and zeros in 3 different layers, R, G, and B. They're just a whole bunch of ones and zeros, a whole mess of them. And somehow from that whole mess, that's not a cloud. From a whole mess, that's not a beetle. From a whole mess, that's not a cactus. And that's not a butterfly. From that whole mess of ones and zeros, somehow it's got to figure out what these things are. And so, Ryan, why don't we show them?
Sure. Here we go.
Okay, so this is what's happening. This is inference on a CPU, and you could see up there where.
Oh, it's in the corner.
Up in the where so it's running on a CPU. It's doing 4.8 images per second. But what are these flowers, though?
Oh, let's have a look.
That's a sword lily. Okay.
There's a bird of paradise.
All right, I believe it.
Moon orchid.
That's a moon orchid. Okay. That's what?
A daisy.
That's a Peruvian lily. Okay. Lots of lilies. A Lenten rose. A sad flower. Oh, I bet that one smells good. It looks like it smells good. This is a bit. Okay, that's what it looks like. A Japanese what?
Anemone.
Okay, ruby-lipped cattle. That was a cow.
I don't know half of these.
Blanket flower. Okay.
Bougainvillea.
So, guys, the computer saw a bunch of ones and zeros, and it classified these images to be those things. Now, here's my theory. 100% of you failed it. I wouldn't have called any of them. I would have just said flower, 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 Flower. That's a flower. That's still a flower. You see what I'm saying? That's a cloud. I don't know what that is. That's an animal.
Yes.
That's Christmas. That's right? And so 100% of us would have failed it. And here's this computer looking at ones and zeros, figuring it all out. Utterly superhuman. Imagine applying this technology to medical imaging. Imagine applying this technology to self-driving cars. Imagine applying this technology to robotics. We can finally write software that allows software to write itself so that it can solve the otherwise unsolvable. Well, the problem is 4 images per second looks fast here, but if 1 billion of us are using it, that's going to be a data center so large it will melt icebergs. And so obviously we can't do that. And so Ryan, show us what joy looks like.
Sure.
That's 1 GPU. And so this is the difference between the fastest CPU in the world versus one of these babies. Now that's a fast car. Okay, here in Munich, here in Germany, this would be a supercar right here. Look how fast that is. I just hope it's still right. And so these GPUs, that's a California poppy,
I'll find
a
one.
yellow iris. Okay? So this is what it looks like on a GPU with TensorRT. Incredible speed up. $562. In this particular network, we sped it up 100 times. This GPU has replaced 100 servers. That's the shocking amount. Imagine all the money you're going to save. Run out and get one right away. Okay, so that's for images. Let's take a look at another one. Well, and so the next one is a technology that's done based on the technology by Deep Brown. They're a startup company in Silicon Valley. And what they've done is this. They've taken basically sonic information and they mapped it into a computer graphics, into an image, and they use CNNs, use image recognition on sound information, and as a result, their deep learning voice recognition is not only incredibly accurate, it's also incredibly fast. Their application is for companies who are with customer service, or they need to make sure that all of the transcription or all the phone calls are done within regulation. It could be in healthcare, it could be in finance, it could be in law, it could be in customer service, hotels, it could be retail. So many different types of companies in the world that can't afford to do voice recognition in the cloud. They have to do it inside their company. And not only that, they want to have the ability to retain the data, the observation from all of the speech, so that they could apply that information to other AIs to enhance their business. And so the thing that Deep Brown does is a voice recognition engine that is just lightning fast. Now the thing that's really great is this, and so we created this demo. It goes so fast, so super real time, that you could literally watch any movie and search for words. Just search for the sound of those words. It's going to listen at super real time. It's going to watch and listen at super real time a movie and find whatever scene we need. Okay, so Ryan's going to show you that. Go ahead, Ryan.
So you might have gathered what we're going to show today. So this is we've transcribed a whole bunch of Game of Thrones, and now we can just go and search through it. So we can find our favorite scenes. No one will take my dragons.
This one's really cool. Is Monty up here? Hey, Monty. So the folks at Columbia,
Cambridge Consulting.
Cambridge Consulting. Why did I have Columbia in my head? Cambridge Consulting created this incredible artificial network, and Monty's going to tell you about it in just a second. But we're going to run it so fast. The inference is done so fast that this artist, this trained artist, is going to be able to collaborate with you. So Monty, first of all, tell us what you guys did.
Sure. So this is Vincent here. It's a combination of many different deep neural network technologies using generative adversarial network technology, but several of them combined. Those processed 8,000 masterpiece artworks from Western art from Renaissance through to current day. 8,000 is nowhere near enough traditionally for deep learning to do anything useful. We're going to generate megapixel images here, and you would estimate we should need at least 1,000 times as much. But because of the generative adversarial nature, this challenge that Jensen spoke about between different networks competing and improving each other, we can squeeze so much more out of the data than might traditionally be viewed possible.
And so just very, very simply, Monty and his guys has trained this network how to basically draw, how to generate art like the great artists, okay? How to draw. And they use this GAN network to basically learn how to draw. And then they used another network. There's 7 different networks, but the other network that they have to create is something that would enhance the resolution of the drawing so that it's many megapixels, so it looks beautiful. Okay. And so why don't you show it to us?
Oh, okay, I'll give you a short demonstration. So if I were just to touch the pen onto the surface, initially we get kind of random noise. There's no possible way you can guess what I'm trying to draw there.
That looks like art.
Inherent in the network. That's 8,000 artists all merged together. But if I sort of went for perhaps a kind of jagged landscape, something like that, you can see in real time as I do that, it's beginning to perhaps colour in. It's getting a hint that the sky is unlikely to be rock coloured. I can begin to draw more detail. It comes through more clearly like that. It's a very, very simple picture. And for example, I've got a couple. It's going from the yellow lines, but I drew a better one earlier that looks a bit more like that. And what's interesting there, if I bring the lines up for you, you can see very, very simple sketch. So this isn't recognizing objects. This doesn't know that it's a, it hasn't been trained just on landscapes. If I go and do something damaging to the picture, you can see it's completely changed its mind on what that is. That's no longer a landscape. And even if I add some kind of super real detail like that moon there, we've now got more of an illustration out of it. It's the same picture. I can go between these two.
Hang on a second. I could do this.
Yeah, go on.
All right, so I could be an artist.
Please.
How do I delete that?
Yeah. Get going.
Delete that. Okay. All right. So.
I think you can see how fast the inference is running here. So this trains overnight on a DGX1 supercomputer. It takes about 14 hours, but it's now running, sort of real-time frame rate inference on a small box here. We've also trained the network with slightly different parameters. So one thing we can try is some slightly different styles.
So it looks a little bit like Picasso, right?
Absolutely.
Got to sign that.
Yeah. Wow.
JH
Yeah.
right there. Okay. That'll be $1,000.
Press the heart.
All right, let me just do
Yeah.
one more.
Let's try a few of those different networks, perhaps.
Okay.
So there's some that'll see that perhaps as a lino print, or that have seen more modern pieces.
Wow.
Colourful. So
That's fantastic. Look at that.
The effect.
Incredibly fun. Okay, good job, Monty. Thank you. Thank the guys for reading. That's so amazing. All right, so you saw some examples of us using deep neural networks to solve problems that otherwise would have been unsolvable in the past. We created a platform that makes it possible for researchers and developers to train their network and develop their network wherever they are. It could be in the cloud, it could be in their data center, it could be on their computer. We created this new TensorRT optimizing compiler that targets the entire range of all the processors that we make. And as a result, sped up deep learning inference by a factor of 50, 100, 150. As a result, saving enormous amounts of money. Well, creating this deep learning network and solving unsolvable problems has led us to solving some of the most challenging and most exciting, and in our belief, the most transformational opportunities in the world. Transportation, as you know, is an enormous industry. It's the fabric of society. It makes it possible, it gives us freedom, makes it possible for us to get around, of course. Two fundamental technologies has now inspired car designers all over the world to do amazing redesigns of what's possible in the future. This is one example. This is the work that is done at Airbus. But if you could imagine, the wing is autonomous. The wing is completely autonomous. There's an autonomous machine inside the wing, and it's a battery-powered wing. The car is autonomous, and it has battery. It's an electric vehicle. If you want to have a flying car, you simply summon your wing. The wing flies to you. You get disconnected from the electric drivetrain. The wing picks you up. And holy cow, imagine the experience. And so people are starting to think about these ideas. People are starting to think about these ideas. From the extraordinary to figure out how can we revolutionize transportation for the last, for the 50-mile range, which is what this is intended to do, to every single day's transportation. And so what we did was we applied ourselves to create a driving network, a driving platform, and create a platform by which the entire transportation industry could adopt to create autonomous vehicles. Our driving platform consists of several layers. The first layer, of course, is the computer. The way you compute for an autonomous machine is fundamentally different. Second is an operating system that allows it to take information at real time from all the different sensors and process it. And algorithms and libraries we call DriveWorks that exposes the capability of the computer to applications on top we call Drive AV for autonomous vehicles. And the type of algorithms and the type of applications we have to develop is basically in three categories. One, you have to figure out where you are. It's the perception networks. Where are you in the world? Where's everybody else around you? What do you sense? The second is localization. Based on everything that you sense, you have to figure out where you are, where everybody else is, where they're moving to, and track everything around you. And then third, figure out, based on all of that, reason about what to do. You might have to stop, you might have to divert, you might have to turn, follow a route, accelerate, pass another car. There's a whole lot of different actions that you could potentially take. And so we created this platform, this complete platform that is basically drivable. Several thousand engineers at NVIDIA are working on this. This is an open platform. It is fully functional safe when it's done. It is auto-grade. And it employs three fundamental computing approaches. One is deep learning, another is computer vision, and then the other is parallel computing. We have to do these algorithms in a whole lot of different ways, and the reason for that is because we want diversity. These cars are going to allow us to not pay attention and still drive us safely. But if something were to happen, it could be a systematic problem, something in the algorithm. It could be a computer failure. Maybe it just got old. Maybe it broke. Maybe it got bumped into. Even if the computer failed, and even if the algorithm failed, we still have to have a backup that allows us to drive the passengers to safety. Just imagine that. How do you create a computer that when it fails, it still operates perfectly? And so the answer, of course, is both having redundancy as well as diversity. We have to solve the problem. We have to solve the same problem in multiple ways. We have to solve the same problem in multiple ways. One simple example is this. One way for you to avoid hitting something around you is recognizing and detecting everything around you and figuring out where they are, and then simply driving where they're not. Okay? Figuring out where everything around you is, and then driving where they're not. The other way of solving that problem is to teach a neural network to recognize where is it safe to drive. So one way is to detect what is not safe. The other way is to detect what is safe. If we have these two basic approaches for perception, then that provides us some amount of resilience. Algorithms like this over and over again are stacked all over this computer so that we can provide redundancy and resilience. Well, let me show you a home movie. The engineers are working really hard, and the car that we integrate all of this into is called the BB-8. And they're driving all over California, all over the East Coast. There's some 20 cars driving around. And we made a home movie for you. Let's play it now. We created the stack so that we can understand how deep learning works, so that we could help the industry solve one of the greatest challenges in the transportation industry. And then this platform is completely open. You could use all or parts of our platform, whether it's calling on the libraries that we have, developing the libraries completely yourself, programming directly to CUDA, or using our autonomous vehicle applications that sits on top of it. One of the areas that is going to revolutionize society in just an incredible way is ride-hailing. You guys know this very well. The utility of a car is dramatically higher. The convenience of moving around is dramatically higher. More and more people are moving into the urban areas, and so it's less and less convenient to own their cars. And so all of us see this revolution that's happening with ride sharing or ride hailing. The number of companies that are working on the next generation autonomous vehicle transportation services is just all over the world. There's just some really, really exciting work that's being done. Here in Germany, Audi, the work that's done by Daimler. In the United States, Uber, Lyft, of course, Waymo. In China, Baidu. Ford with Argo AI. GM with Cruise. Startup called Zoox, doing really great work. Nutonomy in Singapore. And Yandex in Russia. Just about every single geography in the world, companies are trying to figure out how to make these cars completely drive by themselves without a driver inside. Which basically means this. In the worst case scenario, if a car computer were to fail, the algorithms were to fail, the backup computer will have to complete the mission. The backup computer will have to complete the mission. Even if a sensor were to break, even if somebody were to bump into your rear and somehow dislodge the sensor so it's no longer calibrated, you still have to finish the mission. Because otherwise you would have to say in a very gentle voice, get out. You would have to tell the passengers to get out. Because there's nobody driving the car. You can't take over, there's no steering wheel. And so the level of computation that's necessary to solve this problem is just enormous. And so just to give you a sense, this is a level 2 sensor suite with cameras and radars. And here's a level 5 sensor suite. It has cameras and radars, a lot more of them because they're all completely redundant. And then there's LiDARs that are surrounding this car. This car is just packed with sensors. If you think about the work that it has to do, it has so much more resolution because it has to see further, it has more redundancy that it has to do deep learning on. It's got all these surround LiDARs that has to do point cloud processing. These cameras and LiDARs have to localize in a redundant way. They're tracking all of the objects around the car because it's likely this car is driving in urban areas and there are people crossing the street. These cars also are mapping cars because it's got to update the HD map that the car is driving within as the roads change. There's no driver, and so every single time it has to have complete confidence that it can complete its mission. It has to have enough horsepower so that the path planning and the controls of the car is as smooth as possible. It turns out that in the old world, high-performance engines makes cars smoother. Smoother for acceleration, smoother at idle, smoother at cruising. In the future, the more computational performance you have, the smoother your ride will be. Okay? There's a very similar analogy there. And then, of course, sensors and computers has to be fail-operate, and this computer has to have enough capacity for software to be added to this car. Hundreds of software engineers are developing these cars at the same time. We simply can't guess accurately enough how much computational capacity is necessary. And so this is what they do. This is what it looks like in the trunk. Brand new AI. This brand new AI is an SDK we call Drive IX, Intelligent Experience. We've basically done this. We've fused the AI that drives the car and all the perception layers that senses what's around the car with an AI that's in the car that senses you, the driver, and all of the passengers in the car. The sensing, the perception of what's around the car and what's inside the car, and some basic neural networks that we've already pre-trained to track where your eyes are gazed, where your head is posed, read your lips, understand your words. All of those type of capabilities, gesture recognition, combined with the perception of what the car sees, okay? The combination of that, the fusing of that, It's going to allow our customers to write applications that are really quite magical. You'll literally be able to walk up to the car, and the car knows exactly who you are. And it already adjusted the seats, opens the car, and if you're a passenger, it knows who you are, and it adjusts the seats and changes everything according to your desires. You're walking up to the trunk because you're carrying a whole bunch of bags. It recognizes that you just went shopping. It's you. That food is going to end up in your trunk, which now has plenty of space because of Pegasus, and you're going to put your food in the trunk. Okay? And so all kinds of different scenarios are going to be possible. And so this SDK is going to be available in early Q4, and basically runs on our Drive platform. And as a result, hopefully these cars becomes an AI. Your car is an AI. Okay, so it's an AI car. Knows who you are, understands what you like, it recognizes the situation around you, recognizes that maybe you're dozing off and you shouldn't be. Maybe you're not looking in the direction of some kids playing in the street, and it warns you, says it to you nicely, that you should be looking to your right. Okay, whether it's in autonomous driving mode or not in autonomous driving mode, your car AI will look out for you. Creating the car computer is just one of the extraordinary endeavors that these companies have to take in order to create the autonomous vehicle fleet of the future. It is an absolutely extraordinary undertaking. Software development like it's never been done. Computer deployment like it's never been done. The amount of software we're writing, the amount of AIs we have to develop, and the fleets that are going to be tested all over the world is an extraordinary undertaking. And it has a lot of different pieces. Today I just wanted to show you what it takes to build this self-driving car. Not just a prototype. Building a prototype is fun and easy. But getting ready to deploy the fleet is incredibly hard. First of all, you've got to collect a whole bunch of data, and you have to label them just perfectly for every single country, every single road structure, every single road condition. You do it because it's so important, and you do it because you can. We have hundreds of people doing this at NVIDIA. You take that network and you train it on the supercomputer that we designed. The supercomputer here is called the DGX, and this GPU goes in here. This GPU goes in here. Can we see it? Can you guys see it? Okay. I can't see you guys seeing it. But this is one of the GPUs. There are 8 of them here. 1 petaflops. 1 petaflops. So that's basically a whole wall of computers fit into this one NVIDIA DGX. This DGX is used for training the network. Okay, so we use it to train the network and run training on DGX. But there are so many road conditions, so many scenarios, we simply can't collect data on because we like not to. We don't want to simulate somebody jumping in front of your car at the last moment. There's no sense doing that, and so we decided to create a 3D simulation. Imagine harnessing all of NVIDIA's capability in photorealistic rendering, and we created a simulator for the car to try all of these different scenarios that otherwise would be impossible to do. We call it 3D Sim on DGX. I've already shown you Drive AV on DPX, Drive PX, and then lastly, ReSim. ReSim is a gigantic undertaking, and here's the reason why it's so important to do it. Every single time you update your network, before you put it on the road, you would like to know that it's going to pass in simulation all of the roads in the world. All of the roads in the world. And over a period of time, we're going to collect up enough data, enough videos, for literally every single road in the world. And so we call this super real-time simulation with DGX. And using the new TensorRT3, this is what we can achieve. With just 8 NVIDIA DGXs, Okay, so this is a picture of our Saturn V supercomputer. The reason why they're all intermixed like that is because each one of our DGXs consume about 3,000 watts. Okay, that 3,000 watts, of course, replaces a whole wall of supercomputer of servers, and so we're delighted by that. But we still need a whole bunch more in order to simulate the world. And so each one of the racks consists of about 20,000 kilowatts, 18,000 watts, and that allows us to hold about 6 of them. And so what's going to happen is this. We collect miles and miles and miles of road data. And in this case, 300,000 miles we can simulate on 8 of those in 5 hours. 300,000 miles represents 10% of all of the paved roads in the United States. All of the paved roads in the United States. And so basically, if you could simulate that in 5 hours, we could simulate every single paved road in the United States in basically 2 days. So when we finally develop our software and we want to release it, we can simulate the whole thing in 2 days. Now, of course, that's if you're perfect. The whole point about simulation is to find bugs. And the whole point about finding bugs is sometimes you do find them. And so we have to do this over and over and over again. And that's one of the reasons why we have so many of them, so that we can reduce the resimulation time down to essentially hours. Let me show it to you. Hey, Justin, listen. This is basically us running in real time. This is running on one Drive PX. One Drive PX is doing a really great job. It ignored the wiper, snowy road, recognizes all the pedestrians, the signs. It's doing a great job detecting things, detecting the road. Okay, now let's go to, suppose we want to do this on our DGXs. And this is what's happening. And this is how we take a brand new network, the entire software stack, and because our architecture exactly compatible between Drive PX and DGX, the supercomputer and the car computer is architecturally and software compatible. We take the software stack, we put it on DGX, and we run it at super real time. Okay? And so that, thank you. Thanks, guys. Good job. And so that shows you, give you a sense of what it takes to create a self-driving car. From the training of the neural network on a supercomputer, to the simulation of extreme cases on a supercomputer, to driving on a supercomputer, to testing on a supercomputer, that entire flow is extraordinarily computationally intensive. And so we've plumbed this entire platform end to end, and it's open to our partners and developers all over the world. There are now 145 startups working on the NVIDIA platform. They're building trucks, they're building shuttles, they're building cars, some of them level 4, some of them level 5, some of them for long haul reasons, some of them for the last mile. There are autonomous machines coming from just about every corner of the world. Everything that moves in the future will be autonomously assisted. Some of them will still have drivers, but all of them will have AI. And so hopefully it will be a lot more efficient in the long term, and transportation is going to get reinvented. I mean, there's just some really, really cool things. Mapping companies that are using our platform, they use our cars for mapping, and they use our platform for map generation. So, autonomous machines. The next generation of autonomous machines is super exciting. Let me finish by talking to you about one of the things that we're working on that's super exciting. And this autonomous machine is unlike the autonomous vehicle. And the reason for that is the autonomous vehicle is designed for collision avoidance. Autonomous machines are designed for interaction, which means they largely collide. Collision is one of the most important things that autonomous machines do. Well, we can't afford to have these autonomous machines learn how to interact with the world by being in the world. And so there are two fundamental technologies we have to create. The first is a whole new type of processor. We call it Project Xavier. Project Xavier is in the process of being taped out. We'll have silicon here pretty soon. It fundamentally changes how computing is done. It's really about real-time sensors. It's really about computing in parallel, using computer vision, using sensor fusion, using deep learning. And it has to be incredibly energy efficient. 30 teraops of operations in 30 watts. That's the first piece. The second piece is a simulation environment. We need to create a virtual world, where robots can learn how to be robots. They go into this world and they use reinforcement learning, and they try it over and over and over and over again until they finally figured out how to be a productive and useful robot. Basically, there are three different things. We have to train the network just like we do with the self-driving car. Then we put that network into a virtual environment where the robot is in, and that virtual environment is powered by a supercomputer so it could run at super real time. And when you're done with that network, then you can put it on this processor we call Xavier, jack the AI right into the head, and this robot will literally stand up and start walking. That's our goal. And so in order to make this happen, there are two pieces of technology we have to create. One is Xavier and one is Isaac. I'm going to show you Isaac real quick. Guys, this is the Isaac world. This is Isaac's lab. And this is Isaac learning how to play hockey. Now you can see Isaac has two eyes, and those two eyes are basically deep learning eyes. So Isaac's world is accelerated AI because Isaac has to have AI to start. It has to be able to recognize, perceive the hockey stick, perceive the puck, perceive where the net is, and then it's got to figure out somehow, without us writing any code, what to do. And we gave it a value function, and the value function basically says, if you put the puck in the net, that's good. If you don't put the puck in the net, try again. Okay? And so we allow it to try and try and try. Notice it's doing it right now. It's learning how to, it's learning right there. Now, in order to speed this up a little bit, Gordon, is that you back there?
Yeah, we're just going to switch to full screen, and then we're going to switch to a robot which is trained a little bit more. So the robot we just saw there, it learned to basically hit the puck and no more than that. And then we've got another robot which we've trained for a little bit longer, and this robot's learned to hit the puck. It's just further along the training program. And now it can hit the puck, but it's not very good at getting it in the goal. So to speed up the learning even more, what we really want to do is train it in parallel and learn the aggregate experience of lots and lots of robots.
And so Gordon here, in this case, what's happening is we replicated Isaac and we let them all train, and then we stop it at some point. We take the smartest Isaac. We take the smartest Isaac and we put the smartest Isaac in everybody's head. And then we start it all over again. Okay, you repeat rinse and repeat this over and over and over again, running on top of a supercomputer, and all of the Isaacs, they see the puck, they see the net, they see they see their stick, and they have to figure out how to sink it. Now, ideally, if this world looks like our world, ideally, when we're done, we could literally take the AI that's in Isaac in the virtual world, put it in the physical Isaac, and the physical Isaac will recognize exactly what to do and do it. Okay? All right, so let's have one more example.
So this is Isaac as trained as much as we could get. He's quite good at getting it in the goal. He's not absolutely 100% perfect, but he's pretty good at playing hockey, and his swing is much more convincing, and he's pretty good, yeah.
All right, not bad. Good job. Okay. So autonomous machines, the next adventure for our industry. And we're seeing so much excitement around Isaac. Every research organization we go to, they can't wait to get their arms on Isaac. So we're looking forward to releasing it in the near future. Okay, so today we talked about